Hello. Hey guys, good morning. Welcome to your first session of the day. I'm Vinay. I'm Director of PM for Spark and Zeppelin at HortonWorks. I'm here with my colleague, Jerry. It's easier to say Jerry. This morning I struggled with saying Sesai many times, but call him Jerry. He's been working on Spark for 2 or 3 years. I've been working with Spark for about 2+ years. Today, we are going to talk about topics you need to understand to run Spark in production. This is not an introduction to Spark talk. One of our colleagues at HortonWorks gave a great hands-on intro to Spark yesterday at the meetup. So if you're at that journey where you're just starting with Spark, some of these things may be a little advanced, but they'll come in handy when you're trying to run Spark jobs in production. So in our talk, we'll focus on both two aspects of running Spark in production. Of course, there are more than 2 aspects, but we don't have time. So what we are not going to be covering is sort of like stuff like running with debugging. How do you debug stuff in production? How do you upgrade various versions? What we'll be covering is how do you run Spark securely in production? How do you manage performance and improve performance for Spark jobs in production. So I basically introduced myself, so I'll skip through this slide. But you're more than welcome to sort of like follow me on Twitter, give us some feedback, comments, and tell us what you like to hear in future talks and sessions. So let's dive into what you need to understand about security for Spark, and especially for running Spark in production. So what is the context? So the context here is there is more than one way to run Spark. There are actually 4 ways to run Spark. And these are called deployment modes. What are these 4 ways? One is you can run Spark standalone. In that case, Spark itself is acting as the cluster manager. So Spark is responsible for providing resource management of the cluster. It is creating the executors. It is shutting down the executors. So Spark is acting as the cluster manager. The second way, you can run Spark on Mesos. So in that case, Mesos is acting as the cluster manager. The third way, you can run Spark on Yarn, which is the focus of this talk and focus of the effort we are engaged in at HortonWorks, and where Yarn is providing the cluster management services. And the fourth way, and just for completeness, I want to cover that, is a pseudo mode where everything runs with a single JVM. So it's basically used when you're developing the program within your IDE. You're not going to be running that in production. So let's go deeper on Spark on Yarn. So Spark on Yarn is, again, classified in 2 different ways. And the difference between these 2 ways is how or where the Spark driver runs. And Spark driver is kind of important. When you submit a Spark job, driver takes the job, it breaks down the job assembles the DAG or directed acyclic graph for the job, breaks it down to stages, sends the job converts it into tasks, and schedules those tasks on your cluster. And when you have to get the results back, the results get collected inside the driver. So driver is very important, but where the driver runs, whether it runs inside Yarn, in that case, it is described as Yarn cluster mode, or whether the driver runs outside of Yarn on the client machine. In that case, it's described as Yarn client. So, and Spark, again, is a big project, so it has a lot of different pieces, moving pieces. So, for example, Spark Shell and Spark Thrift Server, they don't run in Yarn cluster mode, they run in Yarn client mode. So with this context, let's double-click on running Spark on Yarn. So when a user submits a job, what happens? They contact the Yarn resource manager, and tell under the covers, the resource manager allocates a special container, and that special container happens to be a Yarn application master for Spark. That application master then requests Yarn to get more executors as requested by the application. And then those executors are spun up on the cluster. If your job is reading from HDFS, then the brown nodes here indicate HDFS, and then the blue nodes here indicate the node manager. And I will skip node manager right here because I'll come back to it in the later part of the slide. So that's sort of like Spark, the context. Now let's get into the security for Spark on Yarn. So security in Spark, just like in any other system, there are 4 pillars of security. Before we go to the 4 pillars, there is a presumption that often we miss out, is that the step 0 of security, which is the network level of security. So just because you have enabled security, please make sure that you have the network level of security first. So the 4 pillars of security are, and how do you do network level of security? This is IP tables, firewall, make sure nobody can get to your cluster by pinging or trace route or stuff like that. So what are the 4 pillars of security? So authentication is establishing the identity of the caller. And in Spark, just like rest of Hadoop, it uses Kerberos, 3-headed dog. And a lot of people don't like Kerberos. But Kerberos is it's a de facto standard for security in Hadoop. And Spark leverages Kerberos for authentication. For authorization, which is establishing based on the identity of the established user in authentication. So in a way, these 4 pillars are kind of sequential. At least the first 2 are. You cannot have access control without establishing authentication. For access control or authorization, both 2 terms are synonymous. It is making sure only the authorized user has access to the resource, and whatever the resource may be. Audit is making sure of the record of all these things, and encryption has 2 flavors, both on the wire or data in motion and when the files are at rest. So let's take a primer into Kerberos because often, because it's complex, a lot of people who are not familiar with it may stumble. So Kerberos is a three-legged dance, or there are 3 parts to Kerberos. There is client, there is KDC, think of it as a Kerberos server, and then the actual service that you're trying to access. So how does it work? As a client, let's say I'm John Doe. I come to Kerberos system using the Kerberos library. I call what's called kinit. I provide my username and password if you're using that as the way to establish your identity. And then you get to your Kerberos server, validate that, and you get to what you're granted if you're successful in authentication is a master key. The master key is TGT, or ticket granting ticket, that is stored locally in the cache on the machine where you just ran kinit. Then if you're trying to access a secondary service, maybe HDFS, maybe Yarn, maybe something else, before you get to that service, your master key, your ticket granting ticket, you take that ticket back to the Kerberos server and grant what's called a service ticket. So all that dance happens under the cover. It's taken care of by the Kerberos libraries embedded within Hadoop, Java, etc. So when you're trying to access a service, for example, name node, before you get to the service, you need to have the name node service ticket. Kerberos libraries under the cover get it for you if you have access to it. And then when you're trying to access name node, there is another type of token that's used in Hadoop called a delegation token. So there are 2 flavors of it, one used for HDFS, the other one for Yarn. So because in this example, I'm talking name node and data node, we're talking about block access tokens. And the reason why the delegation tokens were used, so delegation tokens are not issued by Kerberos, but delegation tokens are tokens based on symmetric key issued by HDFS, and so that you don't have to go to the name node so many, or rather Kerberos server so many times. And the reason for using that was, imagine a big cluster, thousands of nodes constantly making requests. If you go back to the Kerberos server so many times, you'll basically launch a denial of service attack on the Kerberos server. So if you want to go in detail on that, Owen O'Malley, one of HortonWorks founder, and a bunch of people at HortonWorks wrote a paper on this and how this works within Hadoop. Goes in much more detail if you're interested in that. So let's put this context with Spark. So how does Kerberos authentication work with Spark? Step number 1, just like you are doing Kerberos with other stuff, you first do a kinit. And this, by the way, assumes that you have enabled Kerberos in your cluster already. And how do you enable Kerberos? You can do it the painful way, which is manually, or you can do the easy way. And it's not 100% easy, but it's much easier using Ambari. So you can use Ambari, say, enable my cluster for Kerberos, and it does all the steps for you. So assuming that has been done by the administrator, as a user, what you need to do, and you come in, authenticate from your desktop or your gateway node using the kinit command, your service ticket and ticket granted ticket that I described on the previous slide, all that is transparent to you unless you're thinking about it or trying to debug some problems. And then you try to access your cluster. In that case, you're submitting a job to Jan, and the job runs as that user's identity. As part of running that job, you launch some executors. Those executors maybe go to HDFS, read some files. So the executors that Jan launched on your behalf, or in this example, John Doe, are running with John Doe's identity. When they are reading from HDFS or some other data source, John Doe's identity is propagated, so the files are read with John Doe's identity. So in that case, you can see that identity is propagated all the way down, and sort of like strong authentication is enforced. So that's step one of the 4 pillars, which is authentication. Let's take a look at step 2. But before we get to step 2, I've replaced name node on the previous slide with some data source X. So in that case, X could be HBase or Hive. And if you're trying to read the data, same model works if you're submitting a job through Spark Summit. When you're trying to read data from X, the identity is propagated down. So here is an example. I did a kinit as John Doe, and then I ran a Spark Summit command. So let's talk about the second pillar of security, which is authorization or access control. So in this John Doe example, when he submitted the job, there are multiple levels of access control check. Because we're talking about Jan cluster, he submits the job to Jan cluster. The first access control needs to be, and assuming this is network level of security, is being set up, whether the guy can connect to the network level. After that, assuming we are past all that, we are talking about whether the user can submit a job to this particular Jan queue. So on the previous slide where we talked about, where I showed you the example, you can also specify a parameter which indicates the Jan queue to which you are submitting the job. So if you have specified a parameter there, it goes to that Jan queue. Otherwise, it goes to whatever is the default Jan queue set up in your cluster. It first checks, the Jan checks whether John Doe has permission to submit job to this queue. So that's the first level of access control within Jan itself. Assuming the user has permission to launch jobs on that cluster, the executors are created. And if the executor is trying to read from HDFS, the next access control check is within HDFS. And if the user is trying to access a file or a directory, the check is whether the user has access to read those files or directories within HDFS. So in these two examples, with Jan or HDFS, you have choice. You can manage security, or when I say security, I'm implying access control here. So you can manage access control policy within Jan itself. You can manage it with HDFS ACLs or access control list. Both work. An easier way is to manage it centrally from one console, which is Apache Ranger. So that's why it's in the diagram. So in production, you will probably use Ranger. So that's the access control. I'm skipping the third pillar, which is auditing. And the audit story is, before I get into the slide, is the audit story is because jobs are run in this Jan cluster, read from HDFS. If you have enabled audit on HDFS and Jan level, all that audit is available. So you can identify who ran a job, what actions they did it. And if you are using Ranger, because access control was in force at that point, all those actions are recorded. So you get the audit for free from Ranger integration from one console. And that's why I skipped that. So this is the fourth sort of leg of security. And I should say 4A, because I'm talking about encryption for data in motion. I'm not talking about 4B, which would be data at rest. So this is for encryption for data in motion. So there are various channels of communication. So if you're trying to secure a production environment, the first step is you have to identify what those channels are. Next question is, what is going over those channels? Is it control signal? Is it actual data? So I've tried to identify some of those. So in the Spark Summit, you submit a job. It contacts to the Yarn resource manager. Yarn resource manager allocates the application master, assuming you're running Yarn cluster mode, so your driver is within Yarn itself. Then the driver talks to the executors. So the purple arrows here are the control panel, RPC. Once the driver is talking to the executors, it could send some broadcast variables. It could send some files with the job. Then the executors talk to among themselves for multiple reasons, like if you're doing some group by, all the funnel is coming to one executors. And they can also, so for that, which is the orange arrow here, you're doing some shuffle. And for that, block transfer over HTTP protocol is used. If you're trying to read data from an external source, so the green line, imagine reading data from HDFS or HBase. In that case, the protocol specific to that data source comes into play, and and the encryption over that is dependent on what is your actual data source. Then there is the role of node manager that I skipped previously. So in Spark, if you're using shuffle, which is the temporary data between two sort of stages of job, an executor can come and go, but an executor may have produced its output. So for Yarn, what happens is the output is stored within the node manager on that machine where the executor was. And the executor may be gone, but its data is still there, and that data is consumed by the next executor in play, which may be on a different machine. So using the Yarn node manager and Yarn, the receiving executor will read the data from the node manager, and that's the blue line, shuffle data. So on the next slide, I've tried to list what are the different encryption mechanisms for each of those channels we just talked about. So for shuffle data, the blue line on the previous slide, you can use the Yarn-based SSL. For control RPC, you can use Spark.authenticate setting, which uses symmetric key-based encryption. If you're running on Yarn, Spark will automatically distribute, or Spark will leverage Yarn to distribute the keys for that encryption. If you're not using Yarn, you'll have to configure symmetric key on each of the nodes where Spark jobs are running. Another reason why you would run such a job on Yarn. For the shuffle block transfer, you can enable SASL-based encryption using that setting, and SSL-based encryption for that channel is a work in progress. If you're reading data from the data source, the green line, imagine if you're reading it from HDFS, you can use RPC-based encryption. There are two possible encryption algorithms there, RC4 or triple DES. Or if you're using web HDFS, you can also use SSL there. If you're the connection between the driver and the AM, or the driver and executor, when you're sending files there, for Spark can leverage SSL for that path. And I've listed the master setting for that, but you'll also need to specify the key store password, etc. So that's sort of like the encryption channel examples, the settings. What are some of the things you should understand, and what are the gotchas? So far, when we talked about Spark SQL, I did not cover different ways of executing Spark SQL. One is you could launch Spark Shell, execute your SQL commands there. You could write a program using the Spark API. You can execute SQL via Spark SQL that way. The third way is ODBC or JDBC access. So you have a client like Tableau, MicroStrategy, et cetera, connecting to Spark Thrift Server, which then connects to the cluster and then submits Spark job on your behalf. So there are two hops in ODBC, JDBC connection to Spark. The first hop is whatever your BI tool or Beeline or JDBC, ODBC client to Spark Thrift Server. And in that path, you can specify your username and password, tell it that you're John Doe. Unfortunately, the second hop from Spark Thrift Server to the cluster doesn't tell the cluster that John Doe is accessing. It doesn't have the do as, or us security geeks call it the do as. It doesn't have that property working, and there is a bug open for that. The workaround is to use a Spark Shell, use the programmatic API. In that case, you're launching a job as yourself. The other thing is with Spark SQL, granular security, which means row level, column level security, or masking is not available. We are working on a technical preview of this problem with Ranger integration. So if you're interested in that, come talk to me. I'll show you what we have, and then a tech preview of this will be coming very soon. So we'll make this feature available as a technical preview, which is our step one before we go to the GA with this feature. And with this feature, you'll bring sort of row-level security, filtering, masking. So the use case that will be enabled by this integration would be, like, for example, you have a business user, and they are accessing some business data, and that happens to include SSN, but you only want to show them the last 4 digits. You can do that with this integration. Or you don't want to show them some records, but show them the other records. You can do that with that integration. Spark with HBase, it works with Kerberos, but if you're using a version prior to 1.4 of Spark, there are issues and that have been resolved since then. If you're trying to connect Spark streaming with Kafka on a Kerberos cluster, you'll have trouble unless you're on HTTP 2.4 or later. If you have a Spark job running for more than 72 hours in a Kerberos environment, there is an issue with Kerberos token that was not renewed before Spark 1.5, but that has been resolved. There are still other issues that I haven't listed here, sort of with Spark streaming for jobs running more than 7 days, but we are trying to resolve those as well in the community. So that's sort of like the first half of the talk. Then I'll hand over to my colleague, Jerry.
Hi. Thanks. Hello, everyone. This is Jerry from HortonWorks. In this part, I will introduce some performance tuning guides, especially 2 performance tuning choices when you are running and configuring Spark applications. And these two tuning choices are the most asked questions from our customers. And they will always asked about how to decide which is the better choice. So today, I will give us an introduction about how to choose this. The first choice is big or small executor. Here, as you can see in this slide, this is a command to submit Spark application running on Yarn with the client mode. And we can also specify the number of executors. As we all know, a Spark application is combined by driver and several executors. So here, this parameter is a way to control the number, to specify the number of executors. And followed with these parameters, there are 2 parameters as I marked as red, so executor codes and executor memories. These are 2 parameters to control the size of the executor. We can allocate a small amount of resources, select to specify small values to these 2 parameters. Then we choose the small executor. Also, we can set these 2 parameters to big values. Then we choose big executors. So here the question comes, is there a difference in choosing small or big executor? So how to choose a proper size of the executor? Let me explain in details. So now we have a cluster with 3 nodes. Each node has 24 codes and 96 GB of memory. So totally, we will have 72 codes and 288 GB of memory. So with this fixed amount of resources, like codes and memories, how to choose executor code and executor memory? So as I listed here in a table, we have different choices. So we can choose a small executor size, say like 1 core and 4 GB of memory to an executor. Then with this fixed amount of the cluster resource, we can actually allocate 72 executors running for this application. And then if we increase the size of an executor, then the number can be allocated, will be decreased. And to the extreme, we can put all the resources of 1 node, like here, 24 cores and 96 GB of memory to an executor. Then we can only allocate 3 executors. So as you can see here, the number of executors can be controlled by the first 2 parameters. So now, and with these different choices, actually, from logically saying, the total resource is the same with different choices. But can we say that there's no difference in when we when we actually running applications, there's no difference when we choosing different executor size or how to choose a better executor size. So let me show you a benchmark about different choices. So here I use aggregation benchmark to test with the different combinations. And here you can see the x-axis means the memories per executor. So I choose, this is mapping to the second column of this table. So I choose the memory from the 6 GB to the 108 GB. And the y-axis is the cost per executor. So I choose from 1 cost per executor to the 18 costs per executor. So here I have 6 different choices for the executor size. And with these 6 different choices, actually, we can see the performance result here in the z-axis. This is the processing time, and the processing time is the lowest beta. So as we increase the executor size, so the performance will gradually become better. And at least choice with 3 cores and 18 GB of memory per executor, we will get the best result. After that, when we still increase the executor size, oppositely, the result gradually becomes worse. So from this benchmark result, we can say that first thing is that a very small executor or a very big executor cannot get a good result. That's the one thing I want to deliver. And another thing is that in these four choices, actually the performance is quite close. So as we can know that except 2 small and 2 big executors, the performance is relatively close. So why 2 small and 2 big executors cannot get good performance? For the small executor, the problem is that if you choose a small executor, actually with this fixed amount of resource, you can assign more and more executors, large amount of executors. With this large amount of executors, you will launch large amount of process, and within this process, there are many threads, and this will decrease the CPU efficiency. Also, with large amount of small executors, we will divide the memory into many small zones that will also lower the memory efficiency. So for the small executor, it is not a good choice to choose a very small executor. Also, for big executor, a big problem is that the GC problem. Since we have to manage it, the JVM has to manage a large memory zone. This large memory zone will significantly affect the GC time. That will increase the GC time and will make the application unresponsive. So for the large executor, the big problem is GC. So according to our benchmark or our test, we usually choose 3 to 6 cores per executor and 10 to 40 GBs to executor. And this size is not a very big size, or neither a very big size, nor a very small size. So we now know how to choose a better executor size. Then is it enough for you running a Spark application? And we also should take care of several other things. First thing is that if we're running Spark application on Yarn, actually each executor is mapping to a container. But the memory size of executor is different from the container. Actually, container's memory is combined by 2 parts. First part is executor memory. As we mentioned in the previously, this is controlled by the configuration executor memory. And another part is overhead memory. This part of memory is off-heap memory used for shuffle fetch data store, and the size is 10% of the executor memory. So a container memory is combined by these 2 parts. So when you are specifying the executor memory, you have to also consider this overhead memory, and using these two memory and to get the size of the container memory, and then you can calculate number of containers can be allocated on the node. so that we'll get an expected result. Also, the Spark process or the Spark application is not the only process running on this node. You will have young process or HDFS process or many system processes. They all require resources, not only memory but also CPU resource. So compared to the previous table, as I mentioned before, so we now need to leave some memories to the system so that other system will use resources, and that will make this application running more smoothly. So another thing is that we should leave some resources to the other system. We don't want Spark to occupy all the resources. And the last thing is that we also need to enable CPU scheduling if we want to constrain CPU usage of each executor. Because when you specify the executor codes, this executor codes is just a logical limitation. There's no physical limitation for the codes you can use. You always can write a program to running out of all the resources, all the CPU resources. So it will be better to control the CPU usage of each executor using the young CPU scheduling and C group. So now we already introduced the executor, how to choose the executor size. A medium size would be a better choice, and there's still another choice when you are running Spark application. It is a TaskParacin, and this concept is derived from MapReduce. And and as we all know, when we are writing a MapReduce program, we need to specify the reducer number, and we always know that how many number of reducer will be a good choice. And in the Spark area, we also have the same concept. When we are writing a Spark application which involves shuffle, like here, group by key or reduce by key and sort by key, these RDD operators which involves shuffle. So for these operators, you have to specify the number of tasks. So what is the preferable number of tasks? That will be another choice. Let me explain in details of the TaskParacin. Say, as you can see here is a traditional MapReduce paradigm, and we have 3 maps, and each map task will generate an output file. This output file is combined by several partitions, and here we have 2 reducers. Select here our TaskParacin is 2. So each map output will divide into 2 partitions, and each reducer will fetch its own partitions and get processed. So each reducer will process 1/2 of the map output data. So if we increase the TaskParacin, say like we increase the reducer number, what will be changed and what is still not changed? As you can see here, if we increase the reducer number to 3, and here actually number of reducer is the same concept of the TaskParacin. And what is not changed is the map output size. No matter what number of TaskParacin we set, the map output shuffle data size is still the same. But what is changed is that now each reducer only processes 1/3 of the total data. So we can now know that with the increase of the TaskParacin, the number of data to be processed for each task will be decreased. Now we code tasks that process small amount of data. We call it small task, and for tasks which process large amount of data, we call it big task. And there are some advantages for small task. First thing is that small task will mitigate the data skewing problem because data can be distributed more evenly to the many tasks, which every task will just process only small amount of data. So this could alleviate the data skew problem. And another advantage is that with the fixed resource, and if each task processes less data, then the most part of data can be cached in the memory. So that will alleviate disk spill and improve the performance. The bad thing is that for small tasks, especially very small tasks, and with this shuffle outputs, with this fixed shuffle output data, we will have to launch many more tasks. And with a large amount of small tasks, this will increase the scheduler overhead. That's the disadvantage of the very small tasks. But for the big task, we have many disadvantages. First is that too big shuffle blocks, actually, too big partitions will crash the Spark application, because Spark application assumes that each partition should be less than 2 GB the size. And also oppositely, this will easily introduce the data skewing problem and the GC, because now each task has to process more data. So in summary, how to choose a TaskParacin? First, I think we should follow usage of the cluster Paracin. Say if our cluster Paracin is 100 and we only set the TaskParacin to 10, and actually we can only use the 10% of the cluster's Paracin. That is not so efficient. So at least we should follow usage of the cluster Paracin. And then how to choose a reasonable task size? We should consider the shuffle output. And according to the shuffle output to calculate the task size, normally, according to our test, is 128 megabytes per task to be processed is a reasonable size. And also, we prefer small tasks, not too small, just small tasks rather than big tasks, because Spark's, compared to MapReduce scheduler, Spark scheduler is much more efficient. So small tasks will bring in many advantages. So we prefer small tasks rather than big tasks. Now let me show you a benchmark result of different TaskParacin. And actually here we also choose the aggregation workload to run the benchmark. This aggregation workload actually has the data skewing problem. So as you can see, if we choose a small TaskParacin, like here 144, the processing time is quite large. And if we increase the task parallelism, and the performance gradually becomes better. But if we still increase the task parallelism, like 5,760, and the performance gradually becomes worse. The reason why the performance become worse for a large amount of small tasks is that because of the task scheduler's overhead will be bring in. So normally this TaskParacin will be a good choice, like 2 to 4 times more than the cluster Paracin will be a reasonable choice for the TaskParacin. So in conclusion, how to tune a Spark application? Like any other application, like a MapReduce application or any other application to tune. And when you tune a Spark application, you have to know the running pattern of this application. Is it an IO-bound application or is it a CPU-bound application? Better know the patterns before you tune will be a good choice. And then, if you actually no one rule can fit all situations, and you can always figure out a scenario that will break all the rules as I mentioned before. So tuning based on the monitoring result to tune will get a better result and save your effort. And the last thing, the more you know the framework, and for example, the more you know the Spark's internal mechanism, and the better you will get the tuning result because that you know the how Spark implement this thing. So you will have to you will get a better direction to tune. So that's about the Spark performance tuning. Thanks.
Thanks, Sherry. So we are almost out of time, but if you have questions, I'll answer them as long as we are allowed to, and then we can take the questions offline. And if you have any feedback, please give us the feedback. So, yeah, go ahead, please.
Hi, Liam Ellis from WorldPay. I had a question about kind of once you've built the model in Spark, how you would expose that to other services. So for real-time processing, obviously you don't want to necessarily have a Spark context for that. You want to just build a REST API, a very fast predictor. Have you got any best practices you can share about that kind of chat there, that kind of problem?
So there is a very interesting talk by Holland Wilkins, ML Leap, and this is precisely addressing that topic. So it's a talk by Holland, who's a TrueCar employee and a customer of ours. We started talking about this problem last October, and Holland and together, and actually all credit goes to Holland, he came up with the solution. So I'll encourage you to go check that out. Go ahead.
I found it a very interesting talk you held about the performance. It sounds to me like this is something we should automate, right? So this sounds like a lot of work and a lot of insight you need as an analyst to do this.
Yeah.
Right, so is there a movement going on somewhere where we try to make it like, okay, I can say this is a high priority task, and somewhere in Yarn I know this user has this priority, so we'll make it this kind of CPU memory and etc.
We have struggled with this problem. So there is not a concerted effort to solve the problem for a very sort of like, give me the best possible result I can get based on the data, inspect the workload. There is not an effort there, but we are all aware of the problem. So I think talking to customers like you and you guys should voice it. There should be an effort in the community to address this problem. There is some part in the Spark community to address some of the problem. So there is an effort on Tungsten to sort of like get the best performance out in, sorry. We are out of time.